Hello, everyone. Great to see you. I think we're going to have a slightly shorter session today, probably an hour. And today I'm going to talk both about infinite sets. I'm not going to go too deep into infinite sets. I'm just going to scroll through the basics. There was a webinar, I understand, last year that is going into more depth. Let's have a look. COMPOS Y13. And did we do maths exams, matrices? Differentiation. I might not have been, but I'll do a bigger session on sets next time. Perhaps there must be a session on infinite sets from last year. But anyways, yeah. So let's get to it. I'm going to talk about cardinality a little bit, and yeah. So I'm going to share my screen. So, are there more integers than natural numbers? That's a question. Well, some of you already know. I wonder if everyone knows the answer to that question. Are there more integers than natural numbers? I hope everyone understands what's an integer, what's a natural number. Remind you that integers, they're natural numbers. Natural is n, and there's an infinite number of both of them, so no. Okay, I'm glad you said that. So 1, 2, 3, 4, etc. And integers is z, and that's 0, plus or minus 1, plus minus 2, plus minus 3, etc. Yes, of course, there's infinity of both, but still, the question stands: are they the same? Is it the same number, or is it more integers than natural numbers, or like how do we even begin? Like, how do we know if they are the same or there's more of one? Does anyone know? And if you don't, I'm actually very glad, because then we've got a lot to talk about. I was dreading that everyone would say, "Oh, I know this stuff. That's too easy." Okay, so it turns out that there are different types of infinities. Infinities can be countable. Difference of n times 2 plus 1, maybe a formula for the difference. Yeah, you're super close. Look, now how do we know that two sets have the same number of elements? Well, we imagine set 1, set 2, set 1, set 2, and it consists of elements. And set 2 consists of elements. If we can find a mapping or a function that maps each element of the first set onto each element of the second one, we have a one-to-one mapping. If you can find a one-to-one mapping of set 1 to set 2, you can say they have the same number of elements. Okay. So I wonder if we can find out such a mapping. So if the first set is the natural numbers set, if the first set is the set of natural numbers, then set 2 is called countable. If you can map a set onto this set n, then this set is countable. Basically, you can count the elements. And it turns out that there is a mapping for the integers. So if you list all the integers in order, so the integers are 0, 1, -1, 2, -2, 3, -3, etc. And you can map them onto the natural numbers set. 1, 2, 3, 4, 5, 6, 7. So you can map. It's a one-to-one mapping of the integers onto the natural numbers. So that means every single that means you have the same number of elements, basically. So the answer is integers is a countable set. So there are the same number of elements in N and Z. It's weird, but there is a mapping. You can think of a formula. Yeah, you can think of a formula, but can you think of a formula? So don't worry about the formula. I mean, I mean, there is a mapping. Does that make sense? Does that make sense to you, guys? Do you understand that they have equal sides? Basically, if you can enumerate them, then every element corresponds to a natural number, right? That means it's a countable set, and therefore there are the same number of elements in each set. What about the rest? There's 5 of you. Haven't heard from. So there isn't a difference in the number of elements, but there's a particular mapping from set to set. Well, I mean, number of elements is infinity. Right? Basically, we're asking, are these infinities the same? Right? Obviously, you can't count them. You can't. Interestingly, if you exclude all the natural numbers from the integers, you still have the same number of elements left. Right? If you take the integers and you take away all natural numbers from the integers, you still get non-positive integers, which is the same number. But the thing is, if they are of equal size, that means that they have the same number of elements. Yeah. I mean, saying they have the same number of elements is not really exactly correct. It's just more dramatic when you say countable. When you say countable, it's less dramatic than saying, oh, it's the same number of elements. Let's look at the actually, I'm gonna go for problem 1A. 1A. The Hilbert Hotel. You've seen the video for the Hilbert Hotel? You are in charge of an intergalactic conference. You are in charge of intergalactic science conference. And you have a hotel with infinity rooms. Okay, so you have room 1, room 2, room 3, room 4, etc. 1, 2, 3, 4. And there's an infinite bus, an infinitely sized bus arrives, which carries an infinity people, infinity guests. Infinity guests arrive, and you give them all a room. So all the rooms are occupied. So all rooms are occupied. Okay, so you have a person 1 living in room 1, person 2 living in room 2, person 3 living in room 3. Okay, and all the rooms are occupied. Now, everything's fine until the doorbell rings and another person arrives, and they're very important, so you need to give them a room. So what do you do? How do you resolve the issue? You have infinity rooms, and all of them are busy. All of them are occupied. Where do you put the extra person? More person arrives. Ooh, very good, Alexandra. Did you know the answer, or did you think of it right now? Ah, you watched the video. Excellent. Okay. So yes, you move all the people, you move them up a room. And now the first room is empty. So this extra person comes here. This extra person comes into room 1. Person 1 goes into room 2. Person 2 goes into room 3, etc. So everybody knows where their rooms. So you can give everybody has their keys. So you know everybody where everybody is staying. So you have that's fine. Well, it's infinity plus 1. What do you mean by infinity plus 1? That's the thing. Yeah, infinity plus 1 is infinity, but then infinity is not a real number. And when you say plus, what do you mean? Right? What do you mean when you say plus? It's just the new set of people. It has the same number of is also a countable set. Basically, that's what we're saying. Yes, you can phrase it. Infinity plus 1 is infinity. Yes. However, yes, as I said, you have you'll need you can get into trouble proving what is plus when you're working with infinity. What is infinity? That's kind of stuff you study in university, and that's the stuff I entirely enjoy because it's I don't know. I'm a physicist. Why would I? What would I deal with infinities? I'm an experimental physicist, not theoretical. Anyways, now everyone's settled. The one person is happy in room 1, but then infinity more people arrive. So B, infinity more people arrive. Let's say guess it. Well, it's an intergalactic one, so yes. Infinity more guests arrive. What do you do then? If you watch the video, try to refrain from giving out the answer. So what do you do? Infinity. Any ideas? Or is that everyone watch the video? Type 1 if you know, because you watched the video. And type 0 if you don't know. Okay. I've seen it, but I can't remember. That's a good one. I think I refuse to believe when I do. Okay. So what you do is person in room N moves to room 2N. In this way, the first person goes into room 4. So these are the rooms. So first room, second room, third, fourth, 5, 6, 7, 8, 9. So the first person who was in room 1 goes to room 2. The second person who was in room 2 goes to room 4. The third person who was in room 3 goes into room 6, and 4, 5. And now you have all the odd rooms are now free, and there's infinity of them, and you tell every new person goes to room 2n-1. Yeah, assuming they're numbered, right? The people that are arriving are numbered, so you give them the keys according to the number. And first person goes into room 1, second person goes into room 3, 5, etc. Okay, do you get it? Do you understand? Okay, good. Right. And so yeah, now effectively you can say two countable infinities make a countable infinity. If you add two countable infinities, then yeah. All right. Problem 2. Are there more rational numbers than natural numbers? And that's actually a question from the assignment. If you go to the assignment, that is problem 8. This is problem 8 from the assignment. Problem 8 in the assignment. Are there more rational numbers than natural numbers? Well, the rational numbers are, well, there's a lot of them. So all fractions: 0, 1/3, 1/4, 1/5, 2/6, -1/3, etc. So the rational numbers is massive. The set of rational numbers is massive, and there are infinity between 0 and 1. 0 and 1. There are infinity rational numbers. Like if you take 0 and 1, there's infinity rational numbers. Let's say 1/2, 1/3, 1/4, 1/5. Example: 1/2, 1/3, 1/4, 1/5. The list goes on, and all of these numbers are between 0 and 1, and there's infinity of them. Infinity and infinitesimal, yes. And there's an infinite number of rational numbers between 0 and 1. But I will show you that, in fact, the number of rationals and the number of naturals is the same. Effectively, that you can number all the rational numbers. You can devise a table. Yes, you can still map. That is correct. So what we're going to do you're going to start with zero. And then the first row, I'm going to have all the fractions with denominator 1. So 1 over 1 minus 1 over 1, 2 over 1 minus 2 over 1, 3 over 1 minus 3 over 1, 4 over 1 minus 4 over 1, etc. In the second row, I'm going to have all the fractions with denominator 2. So 1 over 2 minus 1 over 2, 2 over 2 minus 2 over 2, 3 over 2 minus 3 over 2, 4 over 2 minus 4 over 2, etc. Okay. Third row, 1/3 minus 1/3, 2/3 minus 2/3, 3/3 minus 3/3, 4/3 minus 4/3, etc. And as you can see, this table contains all rational numbers. I want to do one more row. 1/4 minus 1/4, 2/4 minus 2/4, 3/4 minus 3/4, 4/4 minus 4/4. Right, now you can, does everyone see that this table contains all rational numbers? Because rational numbers are all fractions, all the possible fractions you can think of. Yeah, happy with that? Now we need to eliminate the identical fractions. So for example, 1 first is the same as 2 over 2, is the same as 3 over 3, the same as 4 over 4. Minus, so you need to cross out these. But we can do this as we go along. All right, so what we do is we say this is the first number, the second number, third, fourth, fifth, 6, 7, 8. We cross out this one, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So this way, you will count all the rational numbers. You can count all rational numbers. Skip the ones, the equivalent ones. Skip the ones you have already met. Example, 1 over 1 is equal to 3 over 3. And that's it. So there's the same number of rationals as there are natural numbers. The answer, same number of rationals as natural. And that's bonkers, because I couldn't believe that when I learned that. It's like you take the first You take the interval from 0 to 1, and there's an infinity rational numbers, and yet you can count them. You can count all the rational numbers, even though there's infinity just between 0 and 1. And of course, there's infinity between 1 and 2, etc. So effectively, infinity plus infinity plus infinity plus infinity is still. So adding an infinite number, yes, adding an infinite number of infinities still makes infinity. Like a simple infinity. And I think you're ready for the next one. You're ready for the next question. And the next question is, are there more real numbers on the interval from 0 to 1 than rational numbers? What do you think? Paris, what do you mean? There's numbers in between. There won't be numbers in between, but we will match them all. It's just they don't go in a row. The table contains all possible rational numbers. There are no rational numbers that are not in this table. If you take any two rational numbers, of course, you can find a rational number in between, but it will be on the list, just further down the list. Because, for example, you can look at, I don't know, 1/2. We can look at 1/2 and 1/3. So in between, there is what's in between 1/2 and 1/3? 5/12. 5/12 is certainly in between 1/3 and 1/2. And 1/2 is here, 1/3 is here, and 1/12, the 5/12 is somewhere, well, it's this column is somewhere here, 5/12. It's in there. So yeah, even if you any rational numbers is fine. So what do you think about problem 3? Are there more real numbers? Well, now we're talking just real numbers. So including all the, so it's all the fractions, including the irrational ones. Square root of 2, square root of 3, pi, etc. No, as in no more, or no, you can count them. No, you can't. You cannot count them. The short answer is yes. Yes, there are. There are. There are more real numbers than rational numbers. And I meant natural, but it doesn't matter because they're the same number of rational numbers than natural numbers. Are there more real numbers than natural numbers? Yes, there are more. Even though there's obviously infinity, numbers between 0 and 1, there's still more real numbers than natural numbers. And I'm gonna prove that. You will see this proof many times over, especially if you do a course on pure maths. You don't have to take a degree in pure math, but you'll still study pure maths at at university. You will learn this at university, and it's a tough thing to understand. So it took me took me a long time to get it. I learned the method. I had an exam on this method. I didn't understand this method. And then I had another exam on this method, and I passed the exam, but I still didn't understand this method. Maybe 5 years later, when I finished university, I was like, ooh, that's okay, now I get it. So I'll start today, and hopefully in 5 years' time, you'll get it. No, maybe today. Maybe maybe you're better than me, and then you'll get it today, and that would be great. Okay, so imagine the what's it called? Converse argument. Proof by contradiction. The contrary. Proof by contradiction. Contradiction. Entry. You can count the real numbers first on the interval 0, 1. Imagine you can. So let's label them. So 0. Well, I mean, let's say you have the first number, the second number, the third number, the fourth number, the fifth, 6, 7, 8, 9, 10. Imagine you have a system. You have a system that all numbers are numbered. And the first number is 0.010101010101. It's probably the first number is probably 0000. I mean, whichever system you choose, you're probably gonna start with 0, but we are starting. Okay. Let's say like this. And the first number is 0, 0, 0, 0, 0. 0, 0, 0, 0, 0. The third number is 0. I don't know, 314,529. 314,529 because I don't remember the rest of the numbers. They're all infinite, right? Because any number, any real number is written with infinitely many decimal places. 4, I don't know, it's 0.12, 12, 13, 14, 15, 16, etc. So imagine you've designed this perfect list which contains all the possible real numbers. Is that clear so far? So you have a list of all real numbers. You have a system. I don't know the system, but imagine that this is the beginning of the list. This is the beginning of an infinite list. Do you understand? Uh, 0.9999999, which is actually the number 1. But as it is, we are on the interval from 0 to 1. All numbers start from 0. Are irrational numbers just not well defined, which is why they're uncountable, unless they are well defined? Well, no, they're pretty well defined. Irrational numbers are real numbers that are not rational. That's the difference. Rational numbers, that can be written as fractions. Irrational numbers, those that cannot be written as a fraction. So irrational is well, for example, square root of 2, square root of 5, pi. So they cannot be written as they cannot be written as fractions. Now I take the diagonal. I take the first number of I take the first digit of the first number, first decimal digit, of course, because who cares about the 0? I take the first digit of the second number, the second number of the second digit of the second number, the third digit of the third number. Okay. And I apply +1. Apply +1 to each of the numbers. So this number becomes 1. This number becomes 2. This number becomes 5. This number becomes 3. This number becomes 4. This number, well, it's a 9, so you can't do 10, so it becomes 0. So effectively, you add a digit to each number. And I write down the number, the resulting number. So new number. And I write it 0, 1, 2, 5, 3, 4, 0, etc. So this is a new number, which is different from the first one, because it has a different digit. It's different from the second one, because it has a different digit on the second position. It's different from the third number, because it has a different number on the third position. It's different from the fourth number, because it has a different number in the fourth position, etc. This number is different from all numbers on the list. Therefore, it is impossible to design a list of real numbers. Okay, how well do you think you understand this on a scale of 0 to 10? Nice. Idiot. So the way I designed the new number, I took the first number from the list and I changed the first digit. So it's definitely not the same as the first number. For the second number, I took the second number and I changed the second digit. So it's definitely different from the second number. For the third digit, I took the third number and changed one digit, so it's definitely different from the third number. So it's different from every single number on the list. Therefore, it is not on the list. Therefore, the new number is a new number. So we do not have a list of real numbers, because I've just written one number which is not on the list. So you can always find a number which is not on the list. So this is a contradiction. This is a contradiction. Therefore, it is impossible to list all real numbers. Numbers from 0 to 1. As you can always find a number not on the list. That's it. Okay. Anyone else still not fully following? I do not see. It froze whilst you were explaining how it is not on the list. How would it not appear at some point? So once again, I know it's tough. It's a tough one. So I have a list of numbers, and I take I say I'm going to write a new number, and to do this, I take the first digit of the first number, but I'm changing it by 1. So the new number is different from the first number on the list. For the second digit, I take the second digit of the second number, but I change it. So it's different from the second number on the list. It's different from the third number on the list because on the look, the first number, this first digit is 0, but I have 1, so it's different from the first number. The second digit is 2, so it's different from the second number. The third digit is 5, so it's different from the third number. Fourth digit is 3, so it's different from the fourth number. Fifth digit is 4, so it's different from the fifth number, and so on. I can design a number which is different from every single number on the list. Yeah? Do you understand now? Very good, but not indirectly from the method. Watch the video. I think the video explains it as well. So the video that we have attached. So yeah. A Riemann sphere, a slightly disconnected topic, but it's an interesting concept. If you take a straight line, it's the line of real numbers, x real numbers. So you have 0 here. I don't know, 1, 2, 3, 4. -1, -2, -3, -4, and you have a sphere, a circle. So this is a circle. This is a one or in one dimension, and you draw a line like this. So the line intersects the circle at a different point. Every line intersects the circle at a different point, and you can say that just this point corresponds to this point on the line. So this is 0.5, for example. This is 1. This is 2. This is 3. This is 4. This is -2. So somewhere here is -1, etc. So because every single point on the line is mapped onto a point on the circle. Every point on the line is mapped onto the circle. And it's a one-to-one mapping. Except what? Which 2 points, well, which 2 values correspond to the same point on the circle? Very good. Infinity and minus infinity, plus infinity and minus infinity. No, zero is here. 0 is mapped here. This is 0. But if you do infinity, it's this line, and this line is plus infinity. Plus infinity and minus infinity. They're both mapped onto the same point, which we call infinity. Now, in maths, plus infinity, minus infinity, and infinity are different things. So minus infinity, plus infinity, and infinity are 3 different things. Things in quotation marks, of course. But yes, you can see that in a Riemann sphere, this is a one-dimensional Riemann, well, two-dimensional Riemann sphere, it's mapped onto. Now you can have a Riemann sphere with complex numbers. Complex numbers, and for this you need to take the complex plane. Complex plane, so you have the set of complex numbers. So x, I, y. And yeah, so you know the complex plane, right? So I don't need to explain. So this number corresponds to 2 plus 3i, for example. This number is 2 minus 3i. That was an accident. Minus 2 minus 5i, etc. Okay. This is the complex plane. Plane. And all you need is to draw a 3D picture. So x usually goes to the left, and y usually goes like this, y. This is just in 3D, so I've twisted it. Like this, and you place a sphere. And it's a 3D sphere, of course. And this is a plane. And now if you draw a line from the top to a point on the plane, so for example, if this is 4, this point corresponds to 4. If this point is 2 plus 2i, so this point on the sphere where it crosses corresponds to 2 plus 2i. This point, I don't know, this is -5 plus 2i. And this point on the sphere corresponds to -5 plus 2i, etc. Let's have a look at the same thing just in 3D. So you have the sphere. This is the x-axis. This is the y-axis. And you have a point B. And you can move point B. And the point on the sphere, corresponding point on the sphere moves. Now, for some reason, I can't move it horizontally, but let's, we can, of course, just need to manually change point B. Point B. Okay. Y-axis. I don't know. Does it work? Okay, so we move point B. Okay, we can change that. So it is 2, 3, 0. Okay, here we are. So you can change, you can move point B, and every single point on the plane corresponds to a point on the Riemann sphere. So hopefully that does that make sense? Every point on the complex plane. So this is the complex plane. This is IY, and this is X. Every point on the plane corresponds to a point on this sphere. So this is not exactly sets, but this is demonstration of mappings. Okay, and you have some sort of similar tasks in here. The end. So that any two segments on the plane are equinumerous. So these are the similar stuff. The semicircle and an arbitrary line. So this is like very similar to what I've just done. Actually easier than what I've done. And interestingly, the top of the sphere corresponds to every single point which is infinitely far away. And this, what we call the complex infinity. The infinity, it has the real infinity, the minus real infinity, yes, the infinity, plus infinity, the minus infinity, the positive complex infinity, the negative complex infinity, and all the other infinities you can think of on the plane, which is quite cool. It's a combination of all. So that's like the infinity of infinities. So whenever you say infinity in maths, you need to explain what you mean, right? Because mathematicians don't like it when you don't define things. So yeah, your maths. Love it. Love it or hate it. It's like Marmite. Okay, RLC circuits. So a little bit of RLC today. Let me just check one thing. I'll be back with you. Okay. Yes, I have a few more minutes to talk about RLC circuits. Okay, so let's have a look at this simple circuit. We have a capacitor that is charged, and we close the switch, and we start. Now, if it wasn't for the resistor, which dissipates the energy, energy would flow from the capacitor to the inductor, and from inductor to the capacitor. You would have the charge on the capacitor would change as the cosine. So from maximum to minimum. Now the current in the circuit, how would the current in the circuit change as a function of time? How would the current change? Minus, ooh, very good. Minus sine wave, indeed, yes. Well, I mean, the minus is arbitrary, but yes, current, we know it's the rate of change of charge. Therefore, if this is a cosine wave, it's minus sine. So it's going to go like this. Yeah, happy with that? So if Q equals Q naught multiplied by cos omega t, then I is I naught sine minus I naught sine omega t. Now, if you introduce the resistor though, this is no resistor. And well, let's move this. So rather than removing the resistor, I'm just going to set the resistance to 0. Okay, so I'm charging the capacitor. So I have a capacitor. You know what? I want to build it from scratch. So I have a capacitor. And I need a way to charge it. So I'll need a switch and a battery. We connect it here. And here, so now I can I can charge it up. And I'm going to measure the voltage on the capacitor. So of course, I can discharge it, and now the voltage is 0. Now, if I close the switch, the voltage drops, steps up. It steps up infinitely because the wires have very low inductance. Right? That's why it's not a... If the wires had larger inductance, oh, okay, you need not only an inductor, you need a resistor. So it should. Okay, so let's. Oh no! Oh no! Is it Control Z? There's no Control Z. Okay, here you have a capacitor and a switch. Like in real life, so this is like a modeling a real life situation. All wires have inductance, so they can have low inductance, but not non-zero, and they still have resistance. And if you have a battery, you take the voltage chart and a wire. Let's see. As you can see, the capacitor charges not instantly. Yeah, that's kind of a point. Actually, I think you get the same result if you do it like this. And discharge the capacitor. So, yeah, so you don't need the inductance. Okay, so you just charge the capacitor. It doesn't happen instantly in real life, but sometimes this happens very quickly. So you can, once again, step up. Okay, perfect. Now I need an inductance, so RLC, and a resistor. Let's put the inductor here. And the resistor is like friction. It produces friction in the circuit. And here you need a switch. Bam. So you disconnect the battery. Now the capacitor is charged. So you can see 10 volts here, 9 volts. And now we can close the switch. And you can see the discharges. But because the resistance is quite large, you don't see any repeated motion. So let's set the resistance to 0 and see what happens. Aha, sine wave. To my taste, it's a bit I want a more pronounced sound wave with I want a lower frequency. To lower the frequency, I lower the inductance. Is that low enough? Let's make it 1 Henry and lower the capacitance. No, actually, I want to higher the capacitance and lower the inductance. Still not good enough. lower the capacitance. Okay, now I'm happy. So I'm going to restart the process. Ah, perfect. So this is my oscillating circuit. As you can see, the battery is not connected, it's just oscillating. A higher frequency, and yeah. And now, watch what happens when I introduce the resistance. Now the resistance is 0. Now I just make it 0.1. You can see that. Okay, so let's disconnect. Charge the capacitor again. This is the charge and hence the voltage on the capacitor. So it goes like this. And yeah, let's not forget the 0 ohms. Okay. So this is undamped. Undamped. And this is low damping or underdamped. Underdamped. Have you all done this topic in school? All right, so you know what I'm talking about. Undamped, underdamped. Okay. Now there are 2 more options, and let's explore them mathematically. So we will write Kirchhoff's second law, and the voltage, which says that in any closed loop, the voltage adds up to 0. So the voltage on the capacitor plus the voltage on the resistor plus the voltage on the inductor is equal to 0. Now you just need to figure out which way is what. So let's say the capacitor at this particular moment, the capacitor is charged positively, and the current is flowing that way. The inductor will produce a counter force, so positive and negative, and this would be positive and negative. So capacitor positive, negative, positive, positive, negative, positive, negative. So in fact, it's going to be V on C, that's going to be positive, minus VL and minus VR. That's equal to 0. And so VC is Q over capacitance. Voltage on the inductor is L d I dt. Now di dt is positive, so it's growing. So yeah, that's correct. Minus VR, which is IR. equals 0. Now you can write this as Q over C minus L d squared Q over dt squared. Now the only problem here is that the current is the rate of discharge of the capacitor. Therefore, this is going to be a plus. So I is dq minus dq dt, because the capacitor is discharging at this moment. When I'm talking about this situation, the capacitor is discharging. So the current is the rate of discharge, so it's minus. And then plus dq dt multiplied by R equals 0. So overall, we have an equation. Let's divide by L. Divide by L. We get d squared q over dt squared plus R over L dq dt plus q over C LC. Well, CL and LC is the same, of course, 0. Now we make a substitution. We say omega 0 is 1 over square root LC, and gamma is equal to R over L. So we can rewrite this equation as Q double dot is the second derivative of Q plus gamma multiplied by the first derivative of Q plus omega 0 squared Q equals 0. So this is a differential equation. And if you do further maths, you would learn how to solve differential equations. So you have the characteristic equation, lambda squared plus gamma lambda plus omega 0 squared equals 0. This is a characteristic equation. And then you find the discriminant is gamma squared minus 4 multiplied by AC. Well, it's a quadratic equation. So it's b squared minus 4ac, which is gamma squared minus 4 times omega 0 squared. This is the discriminant. And that is okay. Now, if discriminant is positive, is less than 0, it's underdamped. If discriminant is equal to 0, that's critical damping. And if discriminant is greater than 0, that's overdamped. And let's look at the situation. So if gamma squared minus 4 omega 0 squared is less than 0, gamma squared minus 4 omega 0 squared and gamma equals 0, and gamma squared minus 4 omega 0 squared is greater than 0. So gamma is, so that's gamma is R over L, so R squared over L squared is less than 4 over LC. So that is, we cancel that. So if if R squared is less than 4L over C. So if R is less than 2 square root of LC, that's the condition of underdamped. Similarly, R is equal to 2 square root of LC. It's critical, and R is greater than 2 square root of L over C. It's overdamped. I'm hoping that is true. So let's check. So in our situation, we had so capacitance is 0.1 and inductance is 0.1. So in our example, capacitance is 0.1 farad and inductance is 0.1 Henry. So the resistance, the critical resistance for the circuit is 2 square root of L over C. Is 2 square root of L over C. So that's 2 ohms. 2 ohms is the critical resistance. So if I set the resistance to 2 ohms, this should be critical damping. Let's check. Okay, charge the capacitor. Resistance to 2 ohms. Oh, that does look like critical damping. So the definition of critical damping is goes down to 0 in the shortest time possible, with no repeated motion, of course. The critical damping. Critical. And finally, if we talk about overdamped, so let's set the resistance to something reasonable. 4 ohms, 5 ohms, that's fine. Okay. Charge. You can see the difference. I hope you can see the difference of overdamping and critical damping. I'm enjoying this very much. I don't know. It's actually the first time I'm doing this. I have never ever done this in my life, like these graphs. I knew what they are supposed to look like, but yeah, this is overdamped. So this is R is equal to 2 L over C, and this is R is greater than 2 L over C. Yeah. Underdamped is, of course, R is less than 2 L over C. So do try this. I mean, if you're anything like me, it's exciting. Right. I went over I wanted to do just 1 hour today, but it's been an hour and a half. So hopefully you've got something useful today, and I'll see you next week for some more sets. You're welcome. See you.